So thanks to the organizers for having me and having us and everything. It's great to be here. So I've learned a lot already today. I've heard and learned a lot about atomic dark matter, SIDM. I learned about Lyman alpha, which is really interesting, and hope to learn more. Lots and lots of other things. I also learned that an operational definition of being old is, do you know supersymmetry? So let me start by just saying that operationally, I am old enough that I know supersymmetry. If you do not know it, it is a great theory. I found a picture of my Susie class in grad school, which was here. It was really, yeah, brought back great memories. Really, it was wonderful. It's not hard to understand, though, just to thank our organizer. If you want to know how to do supersymmetry, it's very easy. You simply take a particle, in this case, a David, you add a cape, and then it becomes super David or a Stavid. I'm also old enough that I don't just know about supersymmetry, I also know enough. I've been around for some anomalies. Caitlin talked about some that motivated some of my earlier work. And I love anomalies. I think they're great. So what is an anomaly and why do we spend our time thinking about these anomalies? And the first thing I always say, because people are like, do you really want to spend all your time thinking about these anomalies? I'm like, well, you know, it helps us motivate new models, like thinking about dark matter. And then even if those anomalies go away, we go on and we study those models and they're great and they're interesting anyway. And I believe that. I believe that. But anomalies can also be correct. They can actually be true. Things that look like spurious signals can then end up being real important scientific breakthroughs. And that happens too. And that's actually kind of what I want to entertain that possibility today. So a couple examples that happened in my lifetime. One is the age of the universe anomaly. That's what people called it. Why were globular clusters so old? Which we now understand to be dark energy. That was what the resolution of that was. There was the solar neutrino anomaly. Why was the sun producing fewer neutrinos than it should have, which we now understand with neutrino mass. Dark matter on its own predates me, but itself was sort of an anomaly. So I want to keep that in mind as we go forward. So to give a little bit of historical context, let's just, before we kind of like go on and think about modern anomalies, let's take an example of one of these older anomalies and think about how it kind of played out. So the solar neutrino anomaly was, we looked at the sun, not with your eyes, don't do that. And it showed about 1/4 to 1/3 of the predicted flux of neutrinos that was what was expected from the standard solar model. Since I'm in Toronto, I have to show, I'm like legally required to show this abstract of Howard Georgi and Mike Luke. If you can't read it, this is a model about magnetic moments of neutrinos. But they have this great line here. They say, most likely the solar neutrino problem has nothing whatever to do with particle physics. It is a great triumph that astrophysicists are able to predict the number of boron A neutrinos coming from the sun as well as they do, within a factor of 2 or 3. And this is Mike Luke, who is now here at the University of Toronto. And it's always worth remembering, like, when we talk about things and people are like, well, I mean, should we really expect any of these things to be so accurate, like astrophysical uncertainties? It's really good that they're doing as well as they could. We just go back and remember this, because maybe that's us, right? It's just good to keep that in mind. It's also funny when they go on and say, however, that sounds like garbage to them. But one aspect of the solar neutrino data, the apparent modulation of the flux of solar neutrinos with the sunspot cycle, is certainly intriguing. So anyway, so this was sort of like a standard take then, and this is a standard take now. So moving past that then, you don't just have the sort of like, let's say, bad takes of looking at anomalies. There can be bad takes of looking at models too. We have our own biases. Those are great physicists. These are great physicists. There's a solution to the solar neutrino problem in 1990, where they study the MSW effect and its solution of the solar neutrino anomaly. And they come up here and they say, we conclude that the non-adiabatic MSW solution is the most likely explanation of the solar neutrino problem. Blah, blah, blah. The non-adiabatic solution, to translate to our modern language, although don't even use this anymore because nobody talks about it, this is what was referred to as the small angle MSW solution. So this is very, very small mixing angles in the neutrino sector. And in particular, they say, we consider unlikely the large mixing angle solution discussed by Rosen and McGill. We expect the mass matrix neutrinos similar to the Kobayashi-Maskawa matrix in which the non-diagonal elements, i.e. the mixings, are small. And so, it wasn't just that takes on whether the anomaly was true or wrong. It's the takes on the solutions to the anomaly were also wrong. And so there's a lot of wrongness to go around then. There's probably a lot of wrongness to go around now, and we want to keep that in mind. So in the context of models, we're talking about a lot of models. This is like a very, very famous quote. So let me just flash it up here so we can make sure it's into the discussion. All models are wrong, but some are useful. So, you go back and you look at the models they had to solve this neutrino anomaly. Okay, so neutrino mass, good, correct. Neutrino mixing, also correct. The matter effects, real, they happen and they're important. But the most popular solution, wrong, okay? The small angle MSW solution, which was the one that most people spent their time studying, was wrong. It turned out that that was continuously connected in its parameter space to the correct solution, but lots of experiments that you would have thought about doing to study the neutrino, which relied on large angles, I think people were very put off. So like things like CAMLAND, or even the fact that we had Super Kamiokande doing the up-down asymmetry for atmospheric neutrinos were not obviously things that you should be doing because they relied on large mixing angles, which people did not believe in. So then the question we want to ask is like, okay, well, what is our model, which is almost certainly wrong, and is it useful, right? That's the question. Is our model useful, whatever that model is? So before we talk about models, let's talk about our anomalies. These are the anomalies I want to talk about, in particular this one, right? No. This is from SNOMAS, and of course the point is not to highlight any particular thing, but just there are two big anomalies people talk about. There's the Hubble tension, there's the S8 tension. The Hubble tension, which is this, is essentially a disagreement between early universe, quote unquote, early universe measurements, so a combination of Planck and other cosmological data sets that give you an inferred value of 67 for Hubble, and late universe measurements normalized to supernovas normalized by Cepheids, giving you 73, which is now about a 5 sigma. And we have the S8 anomaly where, and this is in the SNOMAS, this is not true anymore, I'll talk about it in a second. Early universe measurements give you a value of about 0.83 for S8, and late universe measurements give you S8 of about 0.77 or lower. And it's about a 3 sigma deviation. And so this, we understand intuitively, this is the rate of expansion of the universe today. And S8 is essentially, for those of you who don't study it, a measure of the amplitude of fluctuations on roughly 8 megaparsec scales. So how big those fluctuations are. So let's start with the Hubble tension. So the Hubble tension, like I said, is a disagreement between the late universe measurements of the expansion rate assuming lambda CDM and late measurements of supernova. And there's a sort of a very nice way of talking about it, which probably predates this, but this is the paper that I love looking at, which is a really influential paper for me in terms of like thinking about this anomaly of how do you think about this, where they sort of rephrase this Hubble tension as a possible horizon problem. And they said, well, look, this, I'm gonna simplify it, but you look, there's this peak here. This peak here corresponds to sort of the sound horizon at the time of recombination. So some sound wave propagated out, then recombination happened. We got a snapshot of that, and that's this size, right? So you have some observer who is here, who's looking at that sound wave, and she's measuring some angular size, and that angular size is just the ratio of whatever this side of the triangle is to this side of the triangle. And so this side of the triangle is basically how old the universe is now, which is set by the current Hubble parameter. And this side, how far that sound wave propagated, was how old the universe was then, set by the Hubble parameter then. So if in my model I know this parameter really, really well, and I measure this angle really, really well, then I can work out what Hubble is, right? So that's the way these people kind of phrased it. They said, look, you measure this angle, you think you know this really well, so you can infer this. But if you want to change this, then you can also change that, right? So if you change the horizon size at recombination by modifying how fast the universe is expanding then and you can modify how fast the universe is expanding now. And so, right away, you can't see it because I copied it from a different slide, but this is Reese et al. 2016. That says right there. This was immediately noted that you could change the sound horizon back then by adding additional energy density, particularly in the form of additional relativistic radiation, and that if you had more radiation, then you could push the Hubble up then, shrink the sound horizon then, and get a larger value of H naught now. Sadly, this doesn't really work anymore. We have a lot more than just a single peak in the CMB. There's a lot of information in the CMB polarization that makes this particular thing not work. But this idea, this sort of general idea of let's add additional stuff during recombination is a sort of very popular approach, whether it's dark energy of some kind or additional radiation or stuff. This is a sort of a nice general approach to solving this problem, is just make this number bigger so I can make this number bigger. So what about S8? So the classic way of talking about S8 was sort of in the same language where you say, aha, there's some early universe measurements of S8. So I take lambda CDM and I extract out what the amplitude of fluctuations is supposed to be at 8 megaparsecs. And then I compare that to people who go out and actually make measurements of fluctuations in galaxies and such things. And so these late current universe measurements are low and the early universe measurements are high. And so it's an early late tension as well. Now that changed a lot last year with the release of the CMB lensing from the ACT collaboration in their DR6 release. And so this is what Ruben was just talking about, which is that you have this nice backlight of the CMB, which is then, passing through all these cosmological structures, most of which are relatively nearby. And so you see that lensing and you can make a measurement of the amplitude of structures, not at, yes, you're using the CMB, but that's just your backlight. Your actual structures you're measuring are late universe structures. And so this whole early late universe, breakdown really broke down in 2023 when the ACT CMB lensing came out in good agreement with the Planck values. And so I think a lot of people were like, oh, these people just don't know how to measure things. There's some problem, it's nonlinear and there's baryons and, we can just, make the plot like this and we'll go on, right? It's important to note though, and this is something I really want to emphasize, which is that there's really no such thing as S8, practically speaking. S8 is like a number that was created by cosmologists to make particle physicists look silly, because we would talk about it. And that's because nobody really ever measures S8, almost, right? People measure something, and then they have lambda CDM, and then they say, okay, I'm going to go to the 8 megaparsecs regime, and I'm going to tell you, based on what I measured, what that value is going to be, okay? So this is a nice plot also from Gerbino et al. 2022, which sort of shows the contribution to the measurements of signals that you get when you're actually going to give me a value of S8, but what actual scales and redshifts are actually contributing to the measurement that you're making. So for instance, CMB lensing gets sort of influence into the sort of its signal from all these redshifts, and the color here is not so great, but basically relatively large scales and a variety of redshifts, whereas say galaxy density is at smaller scales and cluster counts are at yet smaller scales. Well, they kind of switch at the late redshifts. But the important point here is not the specific scales, but the fact that these observations are really looking at different scales, but then they all get together using lambda CDM to quote you one number, then you can talk about it, right? But you actually talk about that number, that lives in scales which are right here, which is sort of at the border of the sort of scales that these different measurements are actually talking about. So we use this number to compare these experiments, but that number is extrapolated using a model, namely lambda CDM, and then it gets applied to do analyses of BSM physics in a way that it really shouldn't be. Slightly better is, here's it's slightly more user-friendly, is a paper from the DES collaboration in 2022, where they gave a power spectrum compared to CDM, lambda CDM, and with error bars as a function, well, it's a power spectrum, so it's as a function of K, where you can actually sort of start seeing that this is not just a single scale measurement, but it's actually a combination of scales. And again, if I put the window function, what the scales that actually go into S8 are, they're this band. So it's not just one set of scales that are going into the DES value of S8. There's also smaller scales, and there's somewhat larger scales also that are coming in here. So with that said, okay, so these are our anomalies. So let's come back to this question about what is our model and is it useful? And so to study these models, to study the models and whether they're useful, I rely on having really amazing graduate students, Cara Giovanetti and Tony Zhu. Cara is on the job market this year, and even though Caitlin told me not to say how great she was because she would like her to come to Canada, I'm going to say how great she is, but that doesn't mean she can't come to Canada. Tony is in his second year. He's also great, but it'll be a while for him. So the model I want to talk about is something called WZDR+. We chose that name because it was catchy and it was easy to say. But let me just tell you what goes into this model. It's a model with dark radiation with some initial temperature. Okay, good. Yeah, that's par, I feel like, in this audience. A dark force to which the dark radiation is coupled. Also, totally nobody's going to yell at me here. And dark matter, which weakly scatters off the dark radiation. And a mass threshold, where the force carrier, for instance, can become non-relativistic. Make these, and I was having a conversation at one of the coffee breaks, is that, one thing that's kind of nice about this is that, I look at this, and yeah, I've got some particular formulation of this, but these ingredients are basically very much like the ingredients that you have in atomic dark matter, where you have a mass threshold, you have a few mass thresholds, but you have mass threshold, you have dark matter scattering off it, you have dark force, you have all these things. So I do think that as we're thinking about things, there is something to think about, the sort of like the unity of the phenomenology of some of these models. And I think that the phenomenology I'm going to talk about is bigger than just what this model is. So what does a mass threshold do for you? So at very high temperature, you've got a bunch of degrees in thermal equilibrium. At low temperature, you have one fewer degree of freedom or two fewer degrees of freedom in equilibrium. So when that happens, there are two big things that happen. One is the dark sector heats up. The second thing that happens is that certain interactions can turn off. So let's talk about the first one. The first one is when a particle becomes non-relativistic, it takes all of its entropy and deposits it into the remaining light particles. We're familiar with this in the standard model, where the electrons and the photons are hot together, and then the electrons become non-relativistic, and all their entropy goes into the photons, and the photons heat up, right? And that's why the photon temperature is much higher than the neutrino temperature, much higher. But because of this transition, it conserves entropy and not energy. It actually leads to a even bigger heating up of the dark sector than you would have thought. And so ultimately, the N effective is time dependent. So what happens is something like this. You could have an energy density which would ordinarily have scaled like a to the -4. So just, relative to the expansion of the universe. And what happens is that you scale like a to the -4, and then you get to some point in the history of the universe where the mass becomes relevant. This is when that particle is depositing all its entropy into the light fluid, and it redshifts a little bit more slowly, and then it redshifts like a to the -4 again. And the consequence of this is that the energy density at the end of the day of all that stuff is actually hotter than it would have been if you had not gone through this transition. It's not just that the stuff heats up, it's that it heats up more than it kind of needed to keep pace. So you actually have, if this is your N effective actually changes when you go through that threshold. So you could be, say, N effective could be 0.2, and then at late times it could be 0.3. It's not just a number, it's a time-dependent quantity. So you can take this question, because we know that radiation is interesting for the Hubble tension, and you can say, well, what does this do? You've got some self-interacting radiation. What does it do? It's going to change Hubble from early to late. And there's long been a sort of mild discrepancy in the Planck data on this, but let's not worry about that. So let's just take the sort of just CMB data, okay, just the CMB data, and you say, okay, I'm going to allow a transition to happen at some redshift. What does the data say? Does it care at all? And you look at this and you're like, well, really, no, it doesn't. There's a very mild nothing, right? There's a little tiny peak here, that maybe it would really a little bit rather have a transition, but mostly no, the data doesn't really care. But what happens if you now say, I would really like this to solve the Hubble tension? If I ask this to solve the Hubble tension, then all of a sudden this very broad thing becomes a very sharp thing. And it actually does become statistically significant that there should be some transition in the dark radiation at a redshift of around 20,000. Right? This is a statistically significant statement, at least within this model, that there is a preference for a change in the dark radiation at a redshift of about 20,000. Let me not overclaim this. I'm not going to say this solves the Hubble tension. It helps it, but it does not solve it. What about S8? Well, we've heard that dark matter interactions can suppress power at small scales. A gentle interaction that scales very much like Hubble was pointed out by these authors a long time ago, that it could suppress power. But if you suppress power to solve S8, you actually suppress power at large scales too, and that was bad. But what happens if you have a mass threshold is that you might have a light mediator allowing sort of an efficient scattering of dark matter off of dark radiation in the early universe. But then when you drop below the mass of whatever this mediator is, then you pick up some additional temperature suppression to the interaction, and this interaction basically turns off. So the same mass threshold that heats up the dark sector also turns off any sort of interactions that are going on. So you have something like this. You can look at a plot of, say, the scattering rate compared to Hubble, which at early times is pretty high, and then at some point, this is the transition redshift. It drops and eventually becomes essentially zero. As a consequence, you get a suppression of power at small scales, but as this scattering gets weaker, the suppression of power gets weaker until eventually you return to lambda CDM at long scales. So let's ask the same question. Okay, I'm going to allow a sort of like scattering dark matter model to have this step in it. What does it do? Well, so this blue curve, sorry to change colors on you, is the curve I showed you before, which is just sort of like the sort of general CMB plus other stuff data set. And now if you add in DES, you get this very sharp, relatively sharp peak that also wants a transition at a Z of about 20,000. And let me be clear, this includes ACT-DR6. So this includes the CMB lensing data. So the CMB lensing data combined with the DES data is telling you that there should be a transition about 20,000. I find this kind of interesting because these are obviously very, very different data sets, but they're both pointing to a transition at the same redshift. As a side comment, I'll just mention that when you do this sort of thing, the value of S8, which is a number which we should not be talking about, is much broader. And this sort of tension between the DR6 ACT CMB lensing data and DES goes away entirely. I can take, for instance, the Hubble solution, so the best fit point that fits the Hubble data alone without even thinking about DES, and plot what does it do for DES, and it gives you a drop-off that looks like this, that looks in a reasonable agreement. So this is not including any DES data at all, just the best fit to Hubble spits out some suppression that will give you a DES agreement. So what is this telling us? What is this all telling us? I come back to this question, is this a useful model? Okay, because it's certainly wrong. Like it's totally wrong. Obviously, it's going to be wrong. But it does tell us some interesting things. One thing it tells us is that the disagreement between the CMB lensing of ACT-DR6 and other direct measurements is a model-dependent statement. It is not a direct conflict of the data. It is really a statement about the model of lambda CDM. This model does solve the SA tension, so at the very least, we know that there is a proof of principle of a model that can do this, and we kind of have the ingredients of what you need. But to me, the kind of cool thing, and this is why I was kind of talking at the break about atomic dark matter, is this all kind of says something. What does it say to me? It says something funny is happening at Z of 20,000, right? Or at a scale of around 30 H inverse megaparsecs for the equivalent scales. And so, this model specifically says, oh, there should be some break in the transfer in the power spectrum at around this scale. But you kind of make sense because you understand why that would naturally kind of solve the SA tension. It's not obvious why this helps the Hubble tension, but it kind of makes sense why it would help the SA tension. And I want to emphasize this again, this is not unique to this model. There are lots and lots and lots of models that are going to do this. And so that kind of unity of scenarios, I think, is interesting. And to come back to Caitlin's point, right? Some level, it's about the transfer function. What is the transfer function? And this is telling, at least to me, is saying a transfer function with this suppression is a really interesting place to look. So, so let me conclude. I think it's a time to take a break from lambda CDM. And so I'll just say, when anomalies, even if they're real, even if these two anomalies are real, it's really confusing what they're pointing us to. And so, I think it's the wrong attitude where we get up and people are like, oh, here's a model that solves one anomaly. And you're like, your model is ruled out by blah. Okay, that model, but we already knew that model was probably wrong, right? What is it? What are these models telling us? What are they kind of pointing us to? What should we be thinking about, especially if we're going to think about forward modeling of dark matter? And to me, these anomalies are robust. I think that they're interesting to think about. And I think that they're suggesting something around 30 megaparsecs is happening. And I would be interested to study what kinds of transfer functions would kind of like naturally give this and what those would then do to our simulation. So I think qualitatively, this is all pointing to some sort of a break around 30 megaparsecs. And again, lots of models give this. I thought that the atomic dark matter talk was a really good example of another example of a model that could do something basically the same thing. And if it doesn't work, you can always get back together lambda CDM. All right, thank you very much.